Very good morning. Welcome to Singapore Laboratory Professionals webinar on statistics in analytical chemistry. My name is Sayan. I'm a manager for Frontier Laboratories, which is a Japanese organization making analytical pyrolysis system. I am one of the director for Singapore Laboratory Forum. Our forum is established in 2017 to connect the laboratory professionals like chemists, biologists, engineers, and technicians for learning, knowledge sharing, and networking. As part of our activities, we organize training on analytical techniques as well as the ISO 17025 components. We organize workshops on special analytical topics. We also have a conference theme on which we are organizing the yearly events. So the collages, what you see in this slide, are some of the events that we have organized in the past. We have corporate partners, Agent Technologies, Frontier Lab, TA Instruments, Waters, LNI, who support our conference plus other technical seminars. Today we will be sharing some of the basic aspects of statistics in analytical chemistry. So we may have a general question why statistics is important in analytical chemistry. As we all know, the decision making and a product conformity assessments are based on the test results that is produced in a laboratory. Therefore, it is important to know how accurate and how precise a data that is produced by an analytical laboratory. Statistical tools help qualifying or quantifying the accuracy and precision of the measurements. And further, it helps to improve the laboratory performance based on the findings. When we do an analysis, we are aiming to get the actual true value or closer to a true value. Similarly, we are also aiming to get consistently a same value or closer to the true value. If you look at the two figures in this slide, the left bottom, the person is able to throw the arrow consistently to the same spot, but this is far away from the actual target spot. So that means the person is able to demonstrate consistency, but the perfection is not there to the mark. If you look at the other picture, the person is able to throw the arrow to the spot as well as consistently to the same spot. So that means they can demonstrate a kind of accuracy and precision in this exercise. So that means one need to understand what is accuracy and what is precision. Accuracy is a measure to learn how close a measured value to the true or expected value. Similarly, precision is a measure to know how close the measured values between the measurements, that is replicates. If you look at the first figure, so the target spot is red circle, whereas the person throw the arrow to the yellow region. That means there is some difference between the target spot and the experimental or the achieved spot. This difference is what will be defined as error, which we will talk later with some more details. If you look at the second slide, the person is able to demonstrate the consistency, but still accuracy something is not accomplished in this case. If you look at the third figure, the person is not able to demonstrate either accuracy or precision. It's all over, but some of them are closer to the target spot. So in analytical chemistry, we cannot focus just on accuracy or precision. We need to achieve a good accuracy and good precision in any measurements. If you look at the four figures at the bottom, the first one shows poor accuracy and poor precision. That means the values are all over and it's nowhere closer to the true value or the target spot. If you look at the second one, slightly improved performance, but still the accuracy is not there and precision is not there too. And similarly, if you look at the third figure, at least the precision is demonstrated, but the accuracy is not there. So the ideal preference would be the fourth one, where we are able to target the spot and consistently same. Okay, so this is what that means. We are looking for high precision and high accuracy measurements. But in reality, it is very difficult to achieve this 100% accuracy. That means it has to measure or evaluate the accuracy of the measurement. So there are three different approaches that can be used for evaluating the accuracy. One is the standard addition or spiking experiment, which can be used to evaluate the recovery. And second one is a bias or certified reference material. You can see how different your actual value from that you are being assessed by a third party. And this is a mandatory recovery to all. Right. Then we analyze this as a known sample and increase with respect to our standard. So then we use this data to calculate the percentage recovery. So where we will be looking at the concentration of the spiked sample and the concentration of the unspiked sample, then the concentration added times multiplied by 100. So that means, for example, if you have a sample with 10 ppb of vitamin B and you spike with 5 ppb of vitamin B, then the sample analysis give 14.6 ppb. The requirement on the recovery, so it should be plus or minus 4%. That means you should achieve. In this case, if we calculate the percentage recovery, it is 92%. So even though it is not bad, but it is not falling the range that's supposed to be. That means the recovery need to be improved. So that means they have to look back some of the analytical steps to see how this can be improved. The second approach is a bias, the error. So error basically is finding the difference between an estimate and actual value. So whenever we do a bias of a method, so if you want to calculate error, so you have the mean values, then the certified value should be subtracted from the mean value. This difference is error. Same can be like reported as percentage error also. In that case, you basically have to multiply this by 100. So for an example, if you use a water CRM certificate and the test value is 102, that means in this case, the difference is 2 ppm. So percentage error is 2%. And as per this certified value, it can be anywhere within 5%. So that means this is within the acceptable. So in this case, we can say they have accomplished or passed the accuracy test. The third approach is a proficiency test or the inter-laboratory exercise. In this case, you are again comparing your experimental value with the multiple analysis and use the mean for your assessment. In this case, we are not looking at the percentage error. We are actually trying to calculate the z-score. The z-score is calculated based on the actual value and experimental value by and dividing it by the standard deviation of the reference material or the PT sample. In some cases, it can be our own method precision. When you achieve the z-score, if it is less than 2, then it is considered satisfactory. When it is between 2 and 3, so the value is questionable. That means they have to improve the method performance. If the z-score value is above 3, then it is unsatisfactory. The whole method need to be properly evaluated and validated before this can be used for unknown sample analysis. So here an example, if we have a CRM for the iron in water, drinking water, you have 100 ppm of iron, okay, with a value of plus or minus 3. So when you analyze, you got 96 ppm. Okay. If you calculate the z-score, it is coming 1.3. In this case, we can see that this is than 2. That means the value is acceptable. Whenever you do the accuracy kind of evaluation, you have to do multiple analysis. So when you do multiple analysis, then you have to calculate an average value or a mean value, which is normally done by Excel in most of the cases, where you are summing up the all individual value, then divide by the number of replicates, then you get this mean value. In some cases, you can also calculate a median value. When you calculate median value, it will take the middle value if it is 5 measurements. If it is 6 measurements, then it may be taking the third and data of the data set. So that means the median can always leave out the extreme outlier. And it may be good in some cases, but in reality, you have to ensure that your mean value and median value are not very different. Otherwise, this will affect your precision. Now, let's look into the precision aspect. So, like I said, we have to get a good accuracy and good precision. So, precision is evaluated by a standard deviation. The standard deviation generally, yeah, you can calculate in Excel, but here is the formula shown. So, what you are basically doing, you have the value and the mean value. So, you square up the difference and sum up the square, then divide by n minus 1, then square root. That is what deviation. So when you want to calculate a relative standard deviation, you have this standard deviation divided by the mean value times 100. So generally, the laboratory prefers to use the term relative standard deviation, which can be easy to really compare with the different set of analysis. Here we have shown an example where how the standard deviation is calculated for a set of data. In this case, this is actually the mass measurement. So you have 7 data. Okay, then you calculate the average. Then each individual value is subtracted from the average. Then you square it up. Then sum up the squares. Then divide by a 7 minus 1. Then square is what you got it 0.051. So when you want to calculate the standard deviation, 0.051 divided by the mean value, then your standard deviation is 0.016. So when you want to calculate relative standard deviation, the 0.016 times 100, that is 1.6%. So instead of saying 0.016, if you tell 1.6 percentage, it's much more easy for the people to understand. So in general, as possible. That means lower or relative standard deviation. So the precision is generally two means. That means one is the repeatability, another one is reproducibility. The repeatability is nothing but calculating the standard deviation or the relative standard deviation, but it is based on the set of data that is produced within the same batch on same day by same person, same instrument. That means it has less number of variables. This repeatability is evaluated by estimating the standard deviation and relative standard deviation. This relative standard deviation reflects the method, instrument, and person consistency. Your repeatability standard deviation may be higher if your instrument is not properly calibrated or the person is not properly trained. So that can be a kind of indication to see how this can be improved. On the other hand, reproducibility is a measure of precision of a method or measurement between the batches or between the days. In general, even laboratories, they may have multiple equipment. Really proves any of the so this validation should cover this validation. The reproducibility is mandate method validation, and it helps to evaluate the method robustness. Like as percentage relative standard deviation between the batches, days, chemists, equipments, and location. So again, recapping the definition for repeatability and reproducibility. Repeatability is instrumentation. On the other hand, reproducibility is the precision. So since you have more variabilities, reproducibility, for example, if your method repeatability is calculated as 5%, method reproducibility can be same or higher. Most of the time it should be higher because there is some contribution coming from other variables. So reproducibility is always expecting to be higher than the repeatability. So if you look at the data set that we have done the repeatability on 3 different days. So the first day it is calculated as 5%, second day it can be 4.5% to 5%. Third day it can be 4 to 6%. We have put the lower side, mostly you will observe the values on higher side. If you are really seeing the smaller values, then the first day one need to be verified. Instead, you may have to do one more run to ensure that first day value is not overestimated. Okay, so far we have talked about accuracy and precision. The accuracy can be evaluated by 3 different approaches. That is standard addition method or recovery method, or second is by using a standard or certified reference material, and the third one is a proficiency test or interlaboratory test. So when it comes to precision, generally we try to calculate the standard deviation or relative standard deviation. Relative standard deviation will be more easy for us to compare for different methods and different data set. So within precision, every laboratory calculates repeatability and reproducibility. Repeatability reflects the method consistency on a given day. Reproducibility reflects method robustness on different days, different people, different instrument. And repeatability will be slightly lower than the reproducibility. Now, it is evident that we cannot achieve 100% accurate result. There will be some difference, and this difference is due to some error. Error can be classified as a gross error, systematic error, and random error. The sources of error can be from sampling, preparation, personal, equipment calibration, reporting, calculation, method, storage, and laboratory environment. So we can really designate these different sources into systematic error or random error, gross error. So you can see most of them are falling within systematic error. That means this can be properly controlled if you have taken required precautions. Whereas the random error will be like two-sided and it's difficult to eliminate, but you can minimize with some stringent QA/QC protocol. Gross error is combination of systematic and random error. Mostly the personal error is what people try to put under this gross error, but the gross error mostly is not widely used terminal. Most of the laboratories, people try to work on systematic error and random error. So when you can have error or the different sources can contribute to the error in analytical measurements, then we require to estimate this to understand how this can be improved. And if your laboratory is accredited laboratory, you have to estimate this combined measurement uncertainty for every test method. So under which you are trying to consider all possible sources of errors by combining the standard deviation of each source error or relative uncertainty by combining the relative uncertainty of each sources. Then you square root, based on which you will get the combined uncertainty. That will tell us how good your method precision is and which sources is contributing more, and is there any possibility to improve or reduce this particular source of error. So when you report any analysis value, when it is reported like 55 plus or minus 4 microgram per gram, the bracket, if it is k equal to k factor is 2, that means this report is really like this result is reported with 95% confidence level. And 55 is the mean value, and 4 ppm is the variation that can go both sides. That means if somebody analyzes this particular material, they should get the result in the range of like 51 to 59 ppm. So in this case, the spread value is based on the expanded uncertainty. So it is actually multiplied by the k factor of the combined uncertainty. So we will talk about measurement uncertainty and its estimation methods in different webinar in future. So t-test is another statistical tool that laboratory tried to use it for some of this data set treatment. This one actually trying to compare the means from two different data set which can come from same population or different population. That's why you have to take the hypothesis either null or research based on the data population. Two different way you can calculate. The first one for one sample test is generally similar to the bias test, whereas for the larger data set, it can be done dependent or independent. These days, we can use even Excel for this type of calculation. So that makes our exercise much easier than in the past. So the one sample test is calculated based on the mean value and comparison value and standard error. So in this case, this is straightforward. But if you are trying to do it for a data set, okay, under this two different hypotheses for two mean values from same population or different population, then probably you have to use Excel. In this case, we have compared two set of data produced by two different laboratories. Okay, so if you look at the individual value, they are a bit scattered. In value, you can see they are very much in comparison. Standard deviation is larger for one case, so that is something the lab need to look at. So the same data has been treated by this t-test, and we found that t-value is the t-value is less than the critical value for OL as well as total. That means these two data set do not have any significance difference. This is what the t-test is used for. In some cases, if you want to see is there any outlier, there is another small method that is based on this grub test. So that maybe we will talk in another session. So this kind of statistical tools are not commonly used for day-to-day analysis. In day-to-day analysis, mostly you will be using standard addition where you will estimate the recovery, or bias where you will use a standard reference material, and you will see your performance against the proficiency test or interlaboratory exercise. All these are used for accuracy evaluation. In the case of precision, usually calculate repeatability, then reproducibility, and most importantly, if your laboratory is accurate, then you have to estimate this combined measurement uncertainty and also the expanded measurement uncertainty. So that will tell us how good your method is, how top